Okay, in this video we are going to do an introduction to partial fraction decomposition. So the main aim for this video is to establish the rules and the principles of how to properly set up partial fractions. So let's go into it. Introduction here. So suppose we have the following example. We want to express as a single fraction want to express 2 over x minus 3 minus 3 over x plus 4 as a single fraction. So then we need a common denominator, which is going to be the LCM of the two. So in this case it's going to be x minus 3 into x plus 4. Then x minus 3 goes into this x plus 4 times. So we're going to have 2 here into x plus 4. And x plus 4 goes here, x minus 3 times. So here we're going to have 3 into x minus 3. Then if we remove brackets in both the numerator and denominator, we are going to have 2x plus 8 minus 3x plus 9 in the numerator. The denominator, we're going to have x squared plus 4x minus 3x minus 12. So if we simplify here, in the numerator we're going to have 8 plus 9 is 17, 2x minus 3x is x. The denominator we're going to have x squared plus x minus 12. So these two expressions are the same. Now so here we have got a polynomial divided by another polynomial. So this here is an example of what we call a rational expression. So a rational expression is an expression where you've got a polynomial divided by another polynomial. So this idea is like parallel to the idea of rational numbers, where you've got an integer divided by another integer. So integers and polynomials have got lots in terms of their properties that is common. Now these two fractions here, somewhat simpler fractions, if you like, this is like a compound fraction. Here these ones are much simpler fractions with linear denominators. The denominator here is quadratic. These fractions here are called partial fractions of this compound fraction. So these ones are called partial fractions. We are going to denote that PF here. So these two here are called partial fractions. So the thing we want to be able to do ultimately is to go from this composite or compound fraction back to those partial fractions there. So we're going to be talking about how to do that. And then this rational expression, the numerator is of degree 1 and the denominator is of degree 2. So when that happens, we call this a proper rational expression. So that's again a bit like in rational numbers, because rational numbers, so basically fractions, if the numerator is smaller than the denominator, then you've got a proper fraction. So in this case, if the degree of the numerator is smaller than the degree of the denominator, then you've got a proper rational number. Let's look at another example. So in B, suppose we have 2x plus 1 plus 7 over 2x minus 1 minus 3 over x. Okay, so again, we're going to want to write this as a single fraction. So first thing I want to do is we're going to express that as a fraction as well. Okay, then the LCM is going to be simply the product of these three. So the LCM is going to be x into 2x minus 1. Then 1 is going to go here, x into 2x minus 1 times. So we're going to have 2x plus 1 times x times 2x minus 1. And then this one is going to go here, x times. So we're simply going to have 7x. And x is going to go here, 2x minus 1 times. It's going to be minus 3 into 2x minus 1. Again, if we remove brackets in the numerator, notice that this is a difference of 2 squares. So that's going to give us 4x squared minus 1. And then if we multiply it by x, then it's going to be 4x cubed minus x, then plus 7 here, x here, minus 6x plus 3. The denominator, we're going to have 2x squared minus x. Then we can simplify this. Actually, maybe we can fit the answer there. So in the numerator, the x's are going to cancel out because we've got 7x minus 6x minus x. So in the numerator, we're just going to have 4x cubed plus 3. In the denominator, we're going to have 2x squared minus x. So again, this is a compound fraction, if you like, and this is the simplified form, if you want to think about it, and these are the partial fractions here. The difference between this and the first example is that our rational expression here is improper because the degree of the expression in the numerator is higher. We've got degree 3x here and degree 2 here. So this one is an improper rational expression compared to the one we did in A. But still, these are partial fractions here. So of course, if you've got an improper fraction, when you resolve it to partial fractions, you end up with a polynomial expression and then partial fraction. So we're going to talk about how to go again from this one to this one there. So how do we get to that? All right, so So want to set up or want to talk about the principles of setting up partial fractions. Okay, so how do you do this? So setting up partial fractions. Then in the next video we'll go into the actual computations of these. Just now we want to talk about the principles. So the first thing is if the rational expression is improper, okay, so if the rational expression is improper, like part B above, then the thing we must do is divide. We must divide first. So when we divide, we can use synthetic division or long division depending on what the case is. So and then otherwise, if the so when we divide first, then the part of the division which is like the remainder over the divisor, then we expand that into partial fractions. Okay, but if the fraction is proper, then we simply resolve into partial fractions after factorizing the denominator. So we're going to have to factorize the denominator. Then once the denominator is factorized, then we set up partial fractions. And these are the principles. So there's going to be three cases here. The first case is if we have got distinct linear factors, okay, then what's going to happen is that to each distinct linear factor, we are going to have a corresponding partial fraction. Okay, there is a corresponding partial fraction. So let's do examples here. So if we had x plus 3 over x into, say, 2x plus 1. Now, so distinct means that the two factors are different. Like here, this factor is different from this factor. Linear means that the highest power of x in each factor is 1. Okay, so that's linear and that's linear. So in this case, the partial fractions, so for each factor, the two factors here, x and 2x plus 1, each one will have a corresponding partial fraction. So the first one is going to be a over x. The second one is going to be b over 2x minus 1. A and b are constants that are to be found, but we're going to do that in the next video. So just for now, we want to make sure that we are happy with how to set up the partial fractions correctly, because if you set up the partial fractions wrongly, then whatever calculations you're going to do are going to be in vain. Okay, suppose this time we have got x plus 13 divided by x minus 2 into x plus 5. So again, we have got two distinct linear factors in the denominator. So the first partial fraction is going to be a over x minus 2, and the second partial fraction is going to be b over x minus 1, and then we find the constants a and b. Okay, the second case is the case where we have got repeated linear factors. Okay, so we have got repeated linear factors. So I'll show you what we're talking about in a moment. Okay, so here I'm going to write each factor has a corresponding partial fraction, and then let's talk about what we mean here. So suppose in this example we have 4x minus 3 all divided by x squared into x plus 2. So the repeated factor in this case is this one here, x squared. So it, if you like, it appears twice. Let's just use examples from integers here. So if we take the example of 8, 8 is 2 cubed. Okay, so it's a repeated factor. Now, if you think about the factors of 8, okay, excluding 1, of course, so factors of 8 are going to be 2, 4, and 8. Okay, so these are 2, and then this one is 2 squared, and this one is 2 cubed. So what is this saying? This is saying if we've got 2 cubed here, then there are actually 3 factors in there. Okay, so this is a repeated factor, but since it's to the power 3, then it's got like 3 factors in it. So if it's to the power 2, then you have got like 2 factors, like 4 has got 2 and 2 squared. So that means this x squared here, there are actually 2 factors there. One of them is x and the other one is x squared. So that's what we mean here by saying to each factor we're going to have a corresponding partial fraction. So that means here there's going to be a partial fraction corresponding to x. There's going to be another partial fraction corresponding to x squared. So let's do the partial fractions of this one then. So that means this is going to be a over x, b over x squared, and then c over x plus 2. Okay, and then we can find a and b and c. Something to note here is that this denominator here is a cubic. If you multiply out here, we are going to have x cubed plus 2x squared. So the highest power is 3, and you can see here we have got 3 unknowns. So that's going to be an important general rule of thumb when setting up partial fractions. The number of unknowns must correspond to the degree of your denominator. Here this was quadratic, so degree 2, and we've got 2 constants. Alright, so let's do another example of repeated factors. Suppose this time we have got 3x plus 4 over x into x minus 2 cubed. So that means here we have got 3 factors. Okay, so we're going to have a over x corresponding to this factor here, then b over x minus 2, c over x minus 2 squared, then there's going to be d over x minus 2 cubed, because we have got that factor repeated 3 times. Then again, if you look at this is degree 3 times x, so this degree 4. We've got 1, 2, 3, 4 unknowns. Okay, then in case number 3, this is the case where we've got irreducible quadratic factors. Okay, so these are quadratic factors which cannot be factorized. Okay, so to each quadratic factor there is going to be a corresponding fraction, partial fraction, corresponding partial fraction to each factor. But the thing, important thing here is that each of these partial fraction must have a linear numerator. So we're going to show you what we're talking about here with a linear numerator. All right, so here are our examples. Suppose we have got x plus 2 into x times x squared plus 1. Now x squared plus 1 we cannot factorize, well, not unless we use imaginary numbers, which we're not doing at this point. So that means this here is an irreducible quadratic factor. This denominator is a cubic, so degree 3. So from what we said earlier, we would expect that when we write the setup, the partial fractions for this, we should have 3 unknowns. So the first one is going to be a over x, and the second one is going to be have a denominator x squared plus 1. In the numerator we are going to have a linear term, b times x plus c, where b and c are unknowns. And then you can see now we've got 1, 2, and 3 unknowns. So that's the difference. Got an irreducible quadratic here, then that is always going to be linear. Okay, suppose this time we have got 2x minus 1 all over x plus 1 into x squared minus 2x plus 5. Again, x squared minus 2x plus 5 cannot be factorized, so it's an irreducible quadratic. So just quickly, to see whether this can be factorized, you need to find the discriminant. If the discriminant is not a positive square number, then this thing cannot be factorized. If it's negative, then it cannot be factorized here. Discriminant, which is b squared minus 4ac, so it's going to be negative 2 squared minus 4 times 1 times 5. So it's going to be 4 minus 20, going to be negative 16. So that tells you that this thing cannot be factorized. Anyway, so our partial fractions then are going to be a over x plus 1 and then x plus 1. Then the other one is going to be again bx plus c all over x squared minus 2x plus 5. All right, so that's how you set up your partial fractions. In the next video, we're going to look at so how do we start finding these unknown constants a, b, and c in this case. But before we do that, let's just list a few applications of partial fractions. Okay, so applications of partial fractions in integrating rational functions. Partial fractions are going to be very handy in working out inverse Laplace transforms. Again, partial fractions will be very useful. There is the so-called Z transforms. Again, in working out inverse Z transforms, partial fractions will be very handy, and in doing working out Laurent expansions in complex calculus. So these are just a few of the applications of partial fractions. All right, so in the next video then we'll start looking at this case of how do you find a and b and c when you have got distinct linear factors. Then there's going to be another video for repeated linear factors, etc.